How you guys doing?
Woo!
All right. That's good. Let's keep it alive. We got a few more weeks left, my friends. Let's keep the pulse going. So we hurried through the moon last time. We're going to make it through Mercury today. Then Mars and Venus next week. Jupiter, Saturn after that. We're going to take a little break to talk about life and looking for other solar systems at some point. And then a little bit of planetary evolution, and that's pretty much all we have. Neptune and Uranus on the way out. But, I've said this every single time, but I'm going to say it again. Uh, Now that we're starting to get into the other planets, like the one we're going to be talking about today, uh, I've never actually been to this place before, so it makes it a little difficult to tell a coherent story about. We will have some pieces that we can plug in, but not only have we not been there, we haven't even put anything down on the surface of this thing, right? We've driven by it a few times, so it's going to be kind of more and more like that as we move further out.
Too hot.
It's actually not the hottest place, believe it or not, which is a little bit weird. We'll talk about that. Um, What makes it so, well, since you brought it up already, what makes Mercury so hard to get to is it's really close to the sun. So if you imagine, the way that we get to planets is it's kind of like throwing a baseball at them. And if you throw a baseball towards the sun tends to want to eat whatever you throw at it. So it's one of the most difficult, what would the word be? Uh, as far as rocket engineering goes, or whatever those people at NASA are doing, it's one of the more difficult tasks that they have to.
Some form of constant thrust propulsion. I mean,
Yeah, it's really hard. Yeah, it's very difficult. So, um, yeah, I wish I'd prepared a slide showing you this outrageous pattern that they're having to weave in order to get this latest spacecraft out there. So they have one right now, which is settling into an orbit finally, but it had to do all these flybys and go around the sun, and it's just been insane. So it's tricky. Um, and so we're going to keep going. Venus is the hottest place. It's really hard for that reason. Also, very difficult. There's been limited actual touching of the thing. Mars a little bit more, so we'll have a bit more to say about Mars. But yeah, the further we get, it's just a lot of observational stuff, but less and less solid evidence to go on. So that's important. The stories we're telling are going to have a lot bigger possibility space in them than perhaps what we've had to say about the Earth or the Moon, which is still, obviously, there's quite a bit of interpretation left to be done. So speaking of the Moon, what would we talk about? What are some loose ends from last week? Yeah,
I mean, we talked about like the the leading theories of how it's formed. I think is it the great impact theory? Great impact.
that's the favorite one right now. Yeah, the Theia impact one. Does anybody remember what are the other options that we went through with the Moon? Maybe write anything down? Yeah.
great splash.
Remind me your name again, by the way.
Jared,
Jared. The Great Splash, is that what you said?
is that what?
Ah, oh, there's a fission one. There's one about it forming in place. I'm not sure about the splash one. Which one are you referring to?
The Earth just yoinked it.
Oh, like the Earth just kind of blebbed it off or whatever?
Not like the moon was going through the solar system and then Earth just yoinked.
Oh, just grabbed it. Yeah, there's that. There's the grab one. Um, Yeah, I don't know. Which one of these, well, I guess you guys don't have a very firm ground to grasp all of these. Obviously, the one that's preferred right now is preferred because, um, well, in some ways it allows them to take the pieces that are in common with the Earth as much as possible, like the mantle pieces, and keep them. Because there are a lot of commonalities between the rocks of the Earth and the Moon, but not so much with respect to the core. So I think that's why it's favored. But it's a little problematic too, because it doesn't have all this water that we have in our mantle. We got a tremendous amount of water in our mantle, and there doesn't seem to be any water on the Moon, which is weird. Um,
Do we
I think all these theories are.
the moon?
What's that?
Do we know if there's water in the moon?
It doesn't seem like it from the samples that have been analyzed so far. It seems like it's far, far less than in our mantle, which is the biggest problem right now. So, what else? Yeah.
Last class we talked about like what can we consider a moon, and then we talked about like tidal locking, and like most moons are tidally locked. Uh, and then with like that talking about moons being tidally locked, even though Venus isn't tidally locked to the sun, it's really close.
It is very close, yeah. So tidal lock, the kind of tidal locking that the moon has can also be thought of as this one-to-one resonance where it's rotating exactly at the same rate that it's orbiting us. Mercury is also tidally locked is one way to think of it, but it's not this one-to-one ratio. It's actually a 3-to-2 ratio. We'll look at that a little bit more. So you can be kind of locked in, but not at the exact same rate as well. Yeah.
I didn't want to ask this at the end of last class, but we've talked about this tidal locking, and that a lot of the moons, especially, exhibit this behavior. But we didn't really talk about if we understand the mechanism by which these celestial bodies become tidally locked. And I don't know if that's something that's understood or if we just kind of skip over it. Or
I mean, I think the best way to think about it is analogous to like a frictional braking situation where they're kind of grinding up against each other. It's a gravitational process.
Mm.
So, depending on, the way that I've kind of explained how to visualize gravity to you guys at an atomic level, I think you can imagine that these atoms are sort of grinding up against one another. They have sort of extended structure, and so you have this braking process that happens. Yeah, Dante.
And so any angular momentum that the object had prior or, to it entering that gravity would have been removed if it had any at all.
Yeah, it'll sort of be ironed out. But yeah, I mean, motion is yeah, motion is interesting. So, you know, you can't. The nerdy way to put this is that energy is always conserved, right? But the reality of the situation is that motion's really always conserved. Energy is hard to imagine as anything other than material in motion at the end of the day. And so you can lose motion, but it always goes somewhere else. So if you have friction that slows you down, what does that mean? Well, it means that the atoms have taken up the motion, actually. The friction is actually grinding, it's turning into heat, but heat turns out to just be this kind of chaotic jiggling of atoms, right? So the motion can move down in scale, it can go up in scale. Yeah, you got something.
Like with the impact theory, if the moon was forming like, I guess almost alongside the Earth in that sense, would that like kind of help explain at least why our moon would be tidal locked, like as it's formed, and then as the Earth is spinning, like would that like the basically like the gravitational pull of the Earth spinning account for why like it's moving so locked into the Earth, if that makes sense?
Yeah, I mean, I think that, yeah, I know that they have to have this happen quite a while ago because the tidal locking takes quite a bit of time to happen. But yeah, I mean, problem with a lot of these theories is that, and anybody who's played with any simulations in any of these sandbox programs will realize this pretty quickly. You can tune things really carefully, so you can have that planet strike however you want in order to get the outcome that you desire, right? And another way, and then it's often reported as like, well, we predicted that the moon would appear just as it appears according to this like Theia model or whatever. The reality is that you can back calculate how these things would have to have happened for that to be the case, which makes a pretty compelling story that it was so. But yeah, you're looking at some sort of glancing blow, which probably had the exact right. I think the idea is that Theia and Earth are kind of on the same trajectory a little bit. They sort of cross each other. They're kind of moving together, and so it's like just the right amount of punch to knock off some of it, but not all of it. that actually, oh God, I wish maybe I'll try to pull up a simulation if I remember. There's some incredible simulations of how this goes. It's actually it's crazy. Like
Simulation I found, and I haven't. I'll try.
it's like splashes through the center of the Earth, basically. It's completely bananas. So, and I think that's necessary because whatever heavy stuff was in Theia must have ended up inside of the Earth, right? It didn't move on and become part of the moon because the moon doesn't have this nice iron core like we do, right? It's actually quite interesting. So, as we go over and look at Mercury, now Mercury looks a ton like the moon, actually. Like if you were to just put them side by side, well, just to preview that, I mean, basically look the same from the outside, more or less. You know, you'd think they were cousins or something. They're very, very different inside, and they think, you know, one of the possibilities with Mercury is that it was also smashed by something, but the way in which these things get smashed is going to really determine what happens at the end of the day. That's the idea, anyways. What else did we talk about in terms of formations? What's yeah.
Well, one theory I heard a while back was what was that? Mars might have been Theia, and it basically just like scratched the Earth, and the material from both the Earth's crust and Mars's crust. They were imagining Mars to be a much larger planet than Earth was at the time. Became the Moon, the debris circling the Earth as the Mars had much more, speed. And then that was why the Moon didn't have any of the deep materials from either planet, because
Interesting.
Mars and the Earth have very similar internal materials comparatively to the Moon, which wouldn't make as much sense. Which I don't know if that's true, but that's one theory I heard a while back, which was
Yeah, I mean,
described as a crackpot theory to me. So,
oftentimes theories are crazy until they're correct. It's often how it goes, unfortunately, or for better or for worse. What else is what are some other possibilities? I know I threw a really far out crackpot theory down at the end. If anybody was paying attention.
I mean, if we throw out the time scale of the universe,
Yeah.
we have these crazy metamorphic processes that can happen.
Yeah. Yeah.
So is it possible that formation of water in the Earth's crust is part of some kind of metamorphic process that we don't quite understand?
Yeah.
And because we're more active in that regard than the moon, even if they were originally made of the same materials, the Earth has been churning and creating these, these water molecules in its crust and its mantle. And the moon just hasn't because it doesn't have that kind of activity.
Yeah, exactly. So this is yeah. Go ahead. You had a question?
Yeah, I mean, so if the moon and Mercury are like visually the same and they both have like water and little ice, what makes the moon and what makes Mercury Mercury?
Well, we'll have to deal with Mercury before we get to the bottom of that. I want to follow up though on Andrew's point here because it's important. So this is actually my favorite formation theory. But like you say, it basically violates the timeline we have for the entire universe, which sounds completely insane. However, this theory that we have that gives us the age of the universe is quite interesting, and I think it's worth pointing out again that for somebody, I have a friend who's 65, and he remembers that when he was in high school, the age of the universe was like 6 billion years old. And then when he was in college, it was like 8 billion years old. And then when I was in college, it was like 12.5 billion years old. Now it's 13.8 billion years old. And it seems like every time we build a telescope, the thing gets older and older. So, maybe 100 years from now, the universe will be 200 billion years old, And if it was 200 billion years old, then you have a very different space in which to unfold the appearance of a body like the moon. And like I pointed out at the end of class last time, the moon, if you actually look at its rate of getting impacted by asteroids, and you tried to date it based on how frequently it actually gets hit by asteroids, and tried to say how long did it take to get all of these craters, you would end up with something like 50 billion years for the moon to look the way that it does. Now that's not even since it was formed necessarily, that's just since it got melted last. So anyways, that's completely far out and beyond the pale, but in some sense, I think it makes the most sense. It's probably my favorite one. But yeah, you'd have to take next semester to understand why I think that the Big Bang is one of the worst pieces of science that sits around so proudly in our mainstream conception of reality. It's very strange. It's actually founded on two pieces of evidence, which are both pretty weak. But we'll deal with that in due time.
Wait, one quick kind of final thought. If Mercury is assumed to be, or sorry, the moon's formation, according to the mainstream theories, because of an impact from a different celestial body.
Mm-hmm.
And I think there's some other planets that we account for in the same way. I can't remember if it's Mercury specifically or not. But is it assumed then, because we talk about how unique our solar system is, that we are a merged system in some sense, where we are unique because we are a combination of more than one solar system?
Well, that's a possibility too that has been entertained from time to time. I mean, it's very, very strange. I don't know if I pointed this out to you guys, but we're one of the few solar systems that doesn't have two stars. So most solar systems, and this is another one of those things that the better our telescopes get, the bigger this ratio gets. So we used to think that, some solar systems had two stars. Then we started thinking, wait, most of them have two stars. Then we started thinking almost all of them have at least two stars, sometimes three, sometimes four stars. And so you have these merged solar systems. So what happened to our partner? Were we one of the weird freaks that never had one? And if we did have a partner, first of all, how does that happen? Do they merge? Do solar systems just merge? Are they born this way? Are the stars the same age? Do some of them die? I mean, you really have to start thinking about the lives and deaths of stars, which is unfortunately the subject of next semester. Because the conventional way that we understand stars to die is that they explode and they leave behind this super dense remnant called a white dwarf for the most part. There's other ways they die too, but we don't see a lot of that happening though, which is kind of strange. And there is some evidence to believe that stars are disappearing all the time, or they're at least going non-luminous all the time. And so what happens if a star goes non-luminous, and it doesn't explode? What does it look like? Well, I've done this thought experiment for you guys before where and it'll make more sense next semester, but what's the difference between a brown dwarf and a star? It's like, at some point, it's one atom, right? Because a brown dwarf is made out of all the same stuff as a star. It's just not big enough to do fusion, right? So there is a ridiculous threshold. It's like the straw that breaks the camel's back, right? Where the difference between a planet, like a brown dwarf, and a star is really this fine, fine line. So I think that it's reasonable to believe that stars probably lose that one atom sometimes and they turn into brown dwarfs. You might gain it back and turn back into stars too. So you might skirt the line between red dwarf and brown dwarf quite a bit in your lifetime as a star, as far as I can tell. At least just considering this on first principles. No one's ever observed this to be the case. But so, where am I going with all of this? Yeah, you have to really start asking. You have to really start thinking about these bodies as perhaps spending different times as different roles in a solar system. Even maybe we still. I guess what I'm trying to point out to you, and this is really heretical, but I think it's quite an interesting thought experiment or possibility. Maybe our partner star is still with us in the solar system. Yeah.
Is it Jupiter?
Maybe it's any one of these bodies. Yeah.
Maybe it's Planet X that's somehow somewhere and has gravitational pull, but we don't know where.
Maybe it's the moon. I don't know, right? I mean, maybe it's Earth. Yeah, I don't know. I think that the only thing that's preventing such a theory from actually being presented and being, making its way into your textbook is the Big Bang horizon, the 13.8 billion years, which Yeah, we just don't have time to deal with that. There's no way I would make it through the solar system if I tried to deconstruct the CMB and the redshift distance relationships for you. But we'll do it next semester, so sign up for next semester. Okay, so yeah, that's a really crazy idea. We'll keep coming back to that because I think there's a lot more evidence that something like that is going on. Anything else about the moon? We didn't really get to talk about exploring the moon. They're trying. Any thoughts on that? Yeah.
What are we like? What are we really looking for? Like to go back.
Why?
What's really the point of going back?
Anybody?
Uh,
Wait, hold on, and then back, yeah.
I read an article about this recently. It was they're looking for like water at the poles, specifically in the like permanently shadowed areas. There's been evidence of like just a tiny bit of water in there.
It is true. Why do they want water?
With a system for fuel and
That's right. Yeah, absolutely. Yeah, so anybody else have thoughts on why in the world we'd want to go back to the moon? I know you do. Hold on one second. Anybody else? All right, Dante.
Well, initially when the Artemis project was announced, its main goal is to build a space station to replace the ISS that orbits at a figure eight between the Earth and the Moon that can be used to basically as a dockyard and a shipyard to build ships in space, starcraft in space, so we don't have to have all these massive thrusters and waste all this fuel getting it out of Earth's atmosphere. The other reason,
Hold on, let's unpack that one first. So I want to make sure everybody understands you. It's really, really, really expensive to get stuff off of Earth into space. Why is that?
It's like really hard to get out of the atmosphere.
The atmosphere is horrible, actually. It's actually, you could really think of it, I know it doesn't feel like it, but it's very liquid-like, actually, in some sense. It's very fluid-like is the right way of putting it. It has a lot of resistance. And so that's why we have to make these needle-shaped rockets, right, to poke our way through the atmosphere. We don't have to do that on the moon. Okay, carry on.
the other reason is because the moon is the closest body to Earth that humans could populate in any particular in any capacity.
Yeah, it's a good test bed, right?
Yeah, it's a much better test environment than like the ISS. So all the same tests that we did on that, like similar tests we do on ISS, we'd have a lot more of that ability on the moon. The third reason is telescopes.
Hmm.
So telescopes, there's the idea of putting telescopes on the moon, so that because even the telescopes that orbit our planet, the Earth, there's still a thin layer of atmosphere even all that far out. So they're like, well, we could get rid of all of that if we just go to the moon. So yeah.
Yeah, so, it's probably a good idea for us to set up a backup hard drive for this planet, right? So we should eventually expect that, if we manage to survive the next 10 years or the next 100 years without starting a nuclear war or something, we're probably going to want to eventually explore, I don't know, even other star systems, right? And the moon is a great place to practice. It's a great place to build spaceships. If Elon wants to go to Mars, it's a great place to practice that.
I hope any rocket that I end up taking into space is going to be made. It's going to be one of the Honda ones.
Is Honda making rockets now?
Yeah, they're making rockets.
They make good stuff. Yeah, I mean, I imagine an entire tourist industry will blossom once they start constructing these things. It's happening. So, yeah, any other reasons to go to the moon?
Money.
Money. Yeah, actually, there's good stuff there. Yeah. So, is it Kaylin? Is that your name?
Ellie.
Ellie. Gosh, there's Ellie and there's an Ella and I'm always mixing these up. And I think there's an Abby as well. Abby, Ella. These are terribly confusing for me. I'm sorry. Ella. All right. The fuel, the water, right? So the water is actually quite useful. So one of the things you want to do is you want to be able to make rocket fuel. The one of the primary components for that is going to come from water. You can get hydrogen off of water very easily, actually. So that's important. That's going to be important wherever we go, because say we end up making this incredible cruise ship that can travel to Mars. How are we going to refuel once we get to Mars, right? Same thing. We're going to have to make the fuel wherever we go. We're going to need to make the fuel on the moon. We're not going to be able to just drive from here to Alpha Centauri without being able to harvest fuel along the way. So these processes need to be hammered out before we can pull off any of this stuff. And those are going to be huge intergenerational projects. They're going to take hundreds, maybe thousands of years to get to other solar systems. So it's no time like the present to start figuring these things out. Thoughts, questions? Anything else about the moon?
Does anyone else see the wolf on the moon?
The wolf?
I noticed the whole man on the
Oh, the man on the moon was the wolf.
pull up the moon. It looks like it's facing down to side profile. Looks like its mouth is open. Yeah.
It's a little blurry, but
Yeah.
Do you know what this the word is for when humans see faces and stuff everywhere?
I know there's a word for it, but I'm forgetting.
It's called pareidolia. Doilia. I don't know how you pronounce it. D-O-I-L. Pareidolia. Doilia? Doila? Pareidolia. Check it out. Anyways, we do that. It's one of the annoying things about humans is that we tend to see patterns where they don't exist. This has obviously got us in a lot of trouble in the past when it comes to making scientific theories for things.
That's why we like cars with things that look like eyes.
Yeah, cars. They look like that's right. Especially those 50s cars. All right, well let's go all the way to the interior. So the first planet that we're going to be talking about other than Earth, surprisingly similar to the moon, which is why I wanted to go there next. Now this is kind of interesting because it's not that much smaller than, sorry, the moon is not that much smaller, it seems, right, than Mercury. But Mercury is really, really dense, it turns out. It's actually something like 5 times as massive as the moon, which is very, very interesting. So similar surface appearance, in particular, having both really, not just being cratered, but the sort of mares, the dark patches are there on both of them. Not a great picture of that here. We'll get to some other ones in a minute. Like I said, it is closer to the sun, but it's still quite a ways from the sun, right? So if you imagine that we are, let's say, we feel pretty far away from the sun. I assume you all aren't cooking to death. We're actually only maybe 3 times as far as Mercury away from the sun. So it's not super close to the sun. What else do we want to say about this guy? People have actually, have you guys seen Mercury, first of all? Who's seen Mercury? Nice. People have been watching Mercury about as long as people have been doing astronomy. So the earliest records go all the way back to the Babylonians, who are our great star catalog astronomers. Of course, the Greeks were writing about Mercury. They associated Mercury with the god Hermes, which is kind of the messenger of the gods and the sort of go-between with the underworld, right? Which makes a bit of sense if you consider Mercury's appearance. So for those of you who've seen Mercury, when did you see it? When and where? But like, what? Do you remember what time of day it was?
oh, it's usually during the day, isn't it?
No, actually.
Oh, I remember
Well,
I saw it December 9th.
do you remember? It was at night, though.
It was December.
So Mercury is really only seen right before sunrise or right after sunset.
Yeah, it was right. It was like we were waiting for the sun to set, and that was like it was like one period where it was like, oh, you can see Mercury now, and then
Now it's gone, right? So that's probably part of the reason why the Greeks associated it with Hermes, right? This it was supposed to be this kind of, he had the kind of winged sandals, and he was very flighty and fast, right? So this thing is only in the sky for just a brief moment when it is. I almost never get to see it because my house is ringed by these ridge lines and stuff. Why is that? Why do you only see it in the morning or at night? Yeah, Ezra.
It's super close to the sun.
Exactly. So this is kind of fun, actually. Venus is a little bit like this too, but not. It's of course much further away, so it's up in the sky a bit longer. But it's also only visible in the morning or in the evening, right? Now, a lot of the ancient people thought, for this reason, that it was actually two different stars, and there was, over the years, over the millennia, there's been a lot of debate amongst people as to whether it was the same star or not. But this is actually really fun. So if you do get one of those little Starfinder apps and you start paying attention to Mercury, and to a lesser extent, maybe Venus is easier. You won't need really an app. Venus is the brightest star in the sky. You can see it very easily. It's really cool because you can see the sunset, and then you can see Mercury or Venus. And when you kind of pin those together and you realize that you're on the exterior with Venus, being interior to you, by seeing that and seeing Mercury or Venus, you can actually start to get a really good sense of place in the solar system, I think. It really puts it in perspective when you realize that the reason those things are setting with the sun is because they're being dragged along with the sun, right? They're interior to you and they're being dragged along. I don't know. Kind of putting this all together and then actually starting to look for Venus and Mercury in the sky really like made me feel like I knew where I was in the solar system for the first time, if that makes sense. So this is kind of well, that's a terrible schematization, but oh, this is better. Let's do this. So what I'm trying to say here essentially is that these things are going to appear, they're going to kind of follow that sunset or that sunrise as it's coming up or going down, right? And so, yeah, it's going to really, really hug the sun is what it comes down to. Now, this means that that Venus actually, or sorry, that Mercury actually passes in front of the sun every once in a while. Now, people heavily debated this idea. All right, so even going back thousands of years, there were some people already arguing that Mercury and Venus orbited the sun. This is long before Galileo and all this stuff. However, people figured that if that was the case, that Venus and Mars should go in front of the sun.
Wow.
Nobody ever managed to really see that happen, especially with Mercury.
Yeah.
Now, why would that be? First of all, can you see it?
The little dot.
Not that dot, but that dot, the even littler dot, right?
The little
It's
black dot.
very, very, very hard to see.
Is it the black one or is that black dot?
It's the black dot down here, yeah.
Yeah.
The sunspots, right? And so people kept confusing the sunspots. So people would make these arguments periodically where they would see a sunspot and they would try to say that it was a transit of Mercury. Nobody really managed to pull this off until the advent of nice telescopes during the post-Enlightenment era. So that was quite unfortunate. And obviously it went unsolved until Galileo and Copernicus. What else did I want to say about this? Oh, well, also people, if you stare at the sun too long, you also will see spots. And I think that this actually led to some false reporting about the transits as well. That's
It
kind
will
of
also go blind.
Yes. Well, if you stare at it it will not work out for you. Which is crazy, by the way, that there's an object in our proximity that you cannot look at because it will burn your eyes out. That's just completely bananas that so much light could come from one place. I mean,
If it wasn't for that, you wouldn't see it all.
it's totally insane. And it's also, hundreds, thousands of kilometers away. It's just, it's hard to, it's crazy. Sometimes I just look up the sun for a second and think this is just totally bananas. Okay, so let's think about the composition of this thing for a second. So, you know, unlike the moon, um, I think it's good to compare and contrast the two a little bit. So we talked about how the moon doesn't have a magnetic field, although it appears like it did at some point in the past, which is also very difficult to rectify with the story of Mercury, because Mercury has a magnetic field, actually. It's one of the, well, other than us, it's one of the only terrestrials that has one. So that's pretty strange on its own. It means that there must be some, well, I'll ask you guys, what does that mean exactly? What does it mean about the interior that it has a magnetic field based on the theory that we've provided? Yeah.
That there's like metals in it.
Okay. What else? What are the metals doing? Are they, what's that?
That they would be like big.
They're moving. Yeah. Yeah.
They're liquid.
They're liquid. Yeah. They're swirling around, right? There's some sort of charged eddies going on. Sloshing conductive stuff, and it's charging through some sort of triboelectric process, right? Some sort of frictional electric, like rubbing a balloon on your head kind of thing, right? There's charge being generated in the interior, and it's patterned with swirls of this material. So that's really interesting. It's, again, really, really interesting because in many other respects, it's essentially identical to the moon, except, and presumably they all happened around the same time in the standard story, but something led to the moon not keeping its magnetic field. Now, the standard story with that is that it cooled off really fast, right? Why didn't Mercury cool off?
Because it's right next to the sun. That's my assumption.
That's not a bad answer. However, Venus is hotter than Mercury, and Venus seems to have cooled off and lost its magnetic field too.
Well, the surface is hotter, I suppose, because of the greenhouse gases. But is its core hotter? Would we know?
We don't know. Yeah, that's a good question. Yeah, yeah.
Would Mercury then be hotter because it has more of an less of an atmosphere?
So let me throw another horrible piece of this puzzle in. So you know how I said, like, it's weird because the moon doesn't have any water in its rocks. Not a lot, anyways. Not much. Guess who does?
Mercury.
Mercury's got a lot of water, actually. It's got a lot of volatiles in general inside of its rocks. So sort of like gassy type things that are coming off. How do they know this? Never been to Mercury, so we couldn't pick up the rocks and bring them back. What's that?
See steam.
Basically, yeah. So Mercury doesn't have a real atmosphere. Like it's not windy. They don't have hurricanes and stuff. But it has this little gassy layer. Now, the reason that they even know anything about that is because there's these X-rays that were coming off of the, for lack of a better word, dark side of Mercury. Now, that's weird because, well, X-rays require, first of all, tremendous amount of energy. And so people were stumped about this for a while, and they're actually still trying to get to the details of this with this new spacecraft that's doing all these orbits right now. But what it came down to was there's an interaction with the solar wind. Remember how we were talking about the solar wind being this really high energy stream of lightweight stuff that's essentially evaporating off the surface of the sun. Well, that stuff is crashing into the evaporating stuff that's coming out gassing from Mercury's surface, and it's smashing into it with such a rate that it's actually causing these collisions where there's these enormously energetic interactions that result in the emission of these X-rays. So yeah, Mercury is super, super weird. It does. It has volatiles inside of it, which is very, very, very strange. Okay, so we have to kind of put all these things together. What else do you notice here? This is actually quite interesting. So this diagram is supposed to illustrate the crust, the mantle, and the core of Mercury.
Core is huge.
It's huge.
It also has no inner core.
It's unbelievably huge. The core occupies about 57% of the volume, whereas on our planet, it's only like 17% of the volume of our planet. So the thing is mostly core, which is crazy. How do they know that, by the way?
They shot sound in it,
No, they didn't, unfortunately. Yeah.
and they assumed
They assume it from
magnetic field.
magnetic field is correlated, but how would you know? How would you know? Yeah, this is good for you guys. Anybody?
They shot light at it.
Is it like the way that I guess like dust or whatever's coming in from space is like moving around it almost, and they can assume like color this or that.
That's close. I mean, it's basically the density, right? So you know how much something, I'm gonna use the word weighs just to be colloquial here. You know how massive something is by the way that it orbits, right? That's from the laws that we did the first few weeks. We talked about how mass scales the orbit of a planet, its speed, all of these things, right? So we know how massive the thing is. You can also get the size of it from its angular diameter and so forth, right? Some basic trigonometry. So you know how much the thing weighs, for lack of a better word. You know how massive it is, and you know how big it is. So volume, mass, you get density, right? That's why I said at the beginning that the thing is super, super dense, right? What did I say? It's 5 times as dense as the moon, actually. Now, the only way to have the thing be so dense is to have a huge piece of metal in the middle of it, because metal is really heavy, right? That's why when you go to the gym or don't go to the gym, the weights are really, really metallic and heavy, right? Because all these big atoms at the bottom of the periodic table are metal, right? Metals are heavy. Now, the fact that we think it has an iron core also supports the idea that it has a magnetic field that's still appreciable, right? Because we talked about how magnetic fields are really good for baking in the magnetism for a planet, right? If you have an electromagnet, you want to amplify it, you can stick a piece of iron in the center of it, and it will stabilize the magnetic field, amplify it to some extent. So, okay, so we have all these pieces of the puzzle. We're trying to make a story for where the heck this thing came from. Well, I'm sure you guys can deduce, maybe, we'll get there in a second. All right, so where are people at with this? They're trying to understand how in the world this thing happened. So the standard story that we've been kind of building out, the standard story for the formation of the solar system was that it started in one place. The sun was a singular sun. It happened all by itself. The planets all basically happened the same way the sun happened. It was some version of gravitational congealment that happened. The planets formed out of the leftovers from what didn't make the star. How in the world do you end up with a planet that is one of the most dense bodies in the solar system, other than us, that's all core and all metal? How do you do that? How do the mainstream astronomers accomplish this? Anybody? Yeah,
They have it not be just metal and then have it be impacted by something and lose all of its not metal stuff.
that's exactly right. Yeah. So the leading formation theory for this guy is that it used to be a lot bigger. It used to be maybe the size of our planet. Maybe its core wasn't 57% of its volume at some points. Maybe it was an appropriate size. And then it got whacked by something, just like the Theia story that we tell about our own moon's formation, right? Not a bad idea. Yeah.
Could if the size of the estimated size of Mercury's core is similar to the estimated size of Earth's core, could that then lead for credence? Sorry, to the impact theory. Could that be part of the general explanation?
Yeah, I mean, I'm not sure that all the planets have to have the same size core or anything like that in order to have evolved.
Just assume that if it, like, by ratio, that it would have been a similar size to Earth.
Yeah. I mean, I think that some version of this is probably accurate, actually. I'm not sure. Okay, so the thing is that mainstream astronomy, being bounded by this 14 billion this year timeline, right, to make the whole universe happen, which is, trust me, extremely fast to make everything happen. It's very, very fast. You know, in order to pull that off, you can't go from something the size of an Earth to something the size of a Mercury without having some devastating catastrophic thing happen. It's got to get whacked by a planet, basically, right? Now, if you have 200 billion years or something, maybe you can just have the thing disintegrate over the course of 200 billion years and go from looking very Earth-like or Venus-like down to something like a moon or a Mercury just by natural entropic processes. Like it's just getting whacked at a normal level by normal amounts of meteors and stuff, and it just
losing its stuff to the sun.
Yeah, it could be just getting cooked off too. I mean,
Pulled in.
all that wind, these high energy reactions. So, I think you just end up. This is the funniest thing about science is it's like, and really just like argumentation and philosophy in general. It's like, it always comes down to the assumptions that go into it when you evaluate theories. Like I'm reading, God, I don't want to bore you guys too much, but I'm reading Max Planck's original work on his theory of heat radiation. And the way that people used to always write these huge treatises is they lay out their assumptions first, and then they lay out the theory that proceeds from the assumptions. And he's got at least one or two assumptions in there that are just patently insane. Like they are just not true. And everybody still uses this theory of heat radiation. And so a lot of times, you can have a really logical, like if most of the book is logic and mathematics that works off of a few assumptions that are made up front, they all still depend on those assumptions, right? So if the assumption that bounds the story that we can tell about a planet like Mercury is that it must have happened in 4 billion years, right? Which is a very short amount of time, believe me. If it must have happened in 4 billion years, that really limits the kind of story that you can tell about it. And so, yeah, the only thing really that I've heard that's even halfway rational to explain why this would happen is that it got whacked. Now, it doesn't get you past the problem that you can't really make a big ball of metal in space by gravity alone. That's a huge problem that nobody's really found a way around, which is perhaps the most troubling piece of the puzzle to me. So you can get dust to stick together with gravity, but you can't get pebbles to turn into boulders with gravity. They just bounce off each other. This has been an insurmountable problem for the accretion theorists about the planetary formations in general. So,
Would you have pebbles turn to boulders?
what's up?
How would you have pebbles turn to boulders?
Well, you have to in order to make one of these happen out of a ball of swirling gas is the problem, right? So this is why I personally, that's why I'm trying to introduce you guys to like the possibility that maybe our fundamental assumption about, the constraints that we put on the universe itself are perhaps unreasonable, right? Because it's much easier to forge something really, really dense inside of something huge as opposed to just have it sort of plop out of a ball of gas, right? A swirling nebula of gas as the star is forming. That's something nobody's really managed to do, and it's the story that's told in your textbook, almost tongue in cheek, but it doesn't actually work. Is the problem? Nobody thinks that it works either. They just sort of say, well, we'll probably, we don't understand it, but how else could it happen? We only have 4 billion years to do this, right? So yeah, making a big dense ball of metal is actually really easy if you're at the center of a star. It's also really easy if you're at the center of something huge like a Uranus or a Neptune or something like that.
Okay. Question.
Yeah.
Could something that massive be that close to the sun?
Well, maybe the sun stopped being hot and big a long, long time ago, that it formed within.
Huh.
It's an idea, but it requires huge timelines is the thing, perhaps, or cataclysmic events that we can't possibly account for. Yeah, I don't know. It's an interesting idea. We'll keep coming across this. There's more to this. This story just gets more interesting the more you know about it. Yeah, Andrew.
Yeah. So I don't know if this is happening in anyone else's brain, but if we're following the assumptions according to the standard timeline of the universe, the Big Bang model, and we're telling the story of Earth and the Moon and Mercury, and how Mercury is very similar to the Moon, just minus a couple of attributes. Are we assuming that Mercury and the Moon were originally part of the same body, and that was the that crashed into Earth, and somehow
No one's saying that. Yeah.
three bodies that are somehow strangely linked to one another?
Yeah, no, I've not encountered anybody saying that. It seems like a reasonable. I think the difficult problem is for standard modelers. Standard modelers are very unfond of capture programs for large
Right.
orbital systems. Um, they're averse to those, I think, because the probabilistic. Again, it all comes back to timeline always. It always comes back to timeline, right? Because you'll say, well, what about, is it possible this was captured at some point? It's like, yeah, it's possible, but it's really improbable. And you're like, well, what does that mean? And you're like, well, a lot of planets or something might swing by and get lost before one was captured. And you're like, well, how many? And it's like, well, maybe 1 in 1,000 or something like that. And so they're thinking, well, how often does another star system swing by with, or how often does a rogue planet just swing by? And it's like really infrequently. And so in order to make that a valid possibility on a probabilistic analysis, you would need billions and billions and billions of years, just probabilistically speaking, for that to happen. Yeah.
I wonder if the you brought up how the oddness of our system, might have been caused by like, another solar system, passing through us or
Yeah.
colliding or whatever.
Yeah.
All that chaos.
Yeah.
This, but that itself would require a longer timeline.
Yes.
Wouldn't it?
Yes.
Just the probability of any solar system.
Yes.
And also, for everything to have cooled and been turned into the state that it is now from that, because you would have to have almost two fully formed solar systems that would have to have passed, collide with each other, and then cooled as this solar system, which takes longer.
Yeah. So maybe instead of like continually apologizing for how heretical this idea is that I keep passing off to you guys, what I'm going to say is that the time scales that would be required for the formation mechanisms that I keep laying down as this alternative, they are outrageously longer than the age of the universe. So, without dismantling the Big Bang, they can't really be taken seriously. And I have no problem doing that, but I don't have time in this course to do that for you. So if you're interested in why in the world I don't find the Big Bang to be a very compelling model, sign up for the next course or talk to me outside of class or email me or something. These timelines that I am requiring to make something like this out of a different body is, hundreds of billions, maybe thousands of billions, in other words, trillions of years, and an enormous amount of time, which is inconceivable to the modern astronomer, essentially. Now, and now that I said that, I'm not going to quit apologizing for it, because for most of the history of modern astronomy, nobody thought the universe had a beginning. This is a very modern idea. It goes back to the 1960s and the discovery of the CMB, essentially. There was some proposals of it, but they came from priests, essentially, before that. So the idea that the Big Bang is a piece of science is a very, very new, relatively speaking, idea. For most of post-Enlightenment, post-Renaissance thought, it was not thought to be the case. And so these timelines are only recently heretical. And I think they're unduly heretical. I know they sound completely insane on their face, if you know anything about standard cosmology, but I don't think that they really are. So anyways, I won't apologize, but I'll keep presenting this possibility that, given much longer timescales, we might have a much more rational explanation for how these bodies form, these extremely dense and extremely old-looking bodies, I might add. I mean, when I look at the moon, just you know, when I just look at it and I compare its age just visually to any of the other bodies, I think, man, that thing looks really old, like really, really old. Like it wouldn't surprise me if it was 100 or 1,000 billion years old. Yeah.
The time you keep mentioning the timescales being ridiculous, but they don't seem that ridiculous to me just because of the simple fact that for a long time in a lot of human history, we didn't think the Earth was that much older than a couple of thousand years old.
Yeah,
Like,
that's
a couple
exactly
thousand,
right.
like 10, maybe 10, 100,000 years old. Like we didn't think it was that old. And the concept that it could be billions of years was absurd.
Yeah.
Because the human mind can't even fathom a million, let alone a billion. But since that's become accepted, I mean, it doesn't seem not surprising to me that trillions would be more accurate.
Yeah, my wife and I we're gonna write our next book about this. And the other thing about it is that it's only crazy sounding in some sense in its overview, but if you actually look at the individual pieces of the puzzle, like I'm going to present to you guys a number of mainstream published literature that discusses how Neptune's transition into Earth's. Like this is a pretty mainstream idea. It's just happening somewhere else, right? It didn't happen here, right? Nobody's like really stitched all these pieces together in such a way. And of course, like you said, um, we we keep, you know, the more time that passes, the older that the universe seems to be. The better telescopes we make, the further we can see, the older the place seems to be. By the way, the newest telescope that we have out there, you know, they thought, you know, it can see, let's say, 13.8 billion years. Well, everybody figured, well, now that it's seeing all the way back to the beginning of the universe, you should be able to see like the baby, you know, galaxies forming and stuff, right? Looks just the same as everything else, right? So everything is totally the same as it is already 14, you know, not total, you know, more or less very mature galaxies. Yeah, Ezra.
You mentioned cosmic background, microwave radiation.
Yes.
Is that what it was?
Yes.
Where do you think that comes from?
Oh, good God. This is a huge conversation. Yeah, it's too big of a conversation. I don't know how to answer that question without like without an entire, at least an entire class. I mean, um, I will tell you this though. I will tell you this with certainty. It has not been directly measured away from the Earth. For sure. So there's been differential measures of it at satellites at L2, which is this Lagrange, this sort of stable points far away from the Earth. They've done these differentials where they basically assumed what its profile was and looked for that sort of noise in all directions and compared 180-degree versions of it. This is where you get that nice heat map that you see everywhere of it. The actual measurements have not been measured away from near, like, low Earth orbit, essentially. So anyways, I'm not convinced that it's cosmic at all, I guess that's what it comes down to. But I can build that argument out, but I have to do it responsibly.
What is like the general theory behind like
there's other problems even on first principles with the general theory of it. So the general theory is that there's this afterglow of this Big Bang moment, right? And more specifically, what happened was that in the story of the Big Bang, what happens is you have this moment when the first atoms kind of congeal out of just loose stuff, whatever the heck the primordial pieces are at the beginning. It's not really worth enumerating them right now. And what happens is the atoms that are there, they're in this gaseous form, like a plasma, essentially. They're not even totally, fully formed atoms in this sense. They start screening the light. So the Big Bang actually starts just like in the biblical story with a bunch of light everywhere, essentially, right? Which is weird because I don't know how you have light without atoms at all. First of all, I've never seen light without atoms before. I don't know why we would think that there could be light without atoms. But if we accept that there was light in the beginning, these plasmatic protoatoms start screening the light out, and some of it gets away, right? And that light which has been traveling, is sort of cooling off. It's sort of getting less energetic over the years, and so after 14 billion years-ish, it just bathes the universe in this kind of glow, right? Which is this CMB. Now, on first principles, the biggest problem with that story is this, and this is at the heart of everything, really. What kind of light, we talked about this at the beginning of the class, what kind of light do plasmas and gases make? They make light. Yeah, think about it. The atmosphere of the sun, for instance. It's a gaseous atmosphere. Does anybody remember? What's the difference between the light that comes from like a heated light bulb, for instance, or a heated iron or a coal, and the light that comes from...
Single color.
It's single colors, yeah. So you can get, depending on the energy state, you can get multiple colors, but they're individual lines, right? There's individual frequencies that come from gases, right? The problem is that the CMB is a black body spectrum. It's one of the most perfect black body spectrums we've ever observed. So that means that it looks just like it has the fingerprints of what happens when you heat up a piece of, like a soot-covered piece of metal in the laboratory, essentially, right? It has this perfect signature of a heated body. That's really, really weird, actually. And we've never seen anything like a plasma or a gas give this kind of fingerprint before. So, anyways, it's a huge discussion. I wanted to talk about at least one last thing with respect to Mercury before we move on. And then, all right, any last little questions?
We should probably move on.
I know, we probably should. Okay, so talked a little bit about this. I mean, that's a pretty cool picture to compare the inner pieces, the interiors, the liquid versus solid portions of the cores. I don't know how accurate this is with respect to, I guess that's fairly, we don't know about Venus, let's put it that way. We also,
Mars is theorized to have a solid core, which is why it doesn't have a very, or like at least a.
yeah, it shouldn't have much liquid, right?
It's considered to be a
Cooled off and dead, eh?
because it doesn't have a very strong magnetic field. That even though we assume that its core is iron, so that's kind of the idea.
That's right. Let's keep going. I wanted to talk a little bit about another fun feature. Oh, this is kind of cool. The moon, with respect to their tilt, with respect to the ecliptic, the plane in which all of the planets orbit, Mercury is almost perfect, which is really quite interesting, right? Again, you know, the way I'm looking at it, maybe this speaks to its age, but it's at the end of the day, if we were to lay out all of the different, Pluto's kind of a good comparison. The planets are all tilted in different ways, which is quite interesting, right? They're all, you know, technically Venus is upside down, which is pretty bizarre, right? This is a real hodgepodge that we have here in the solar system. But in terms of, as you can imagine, that if you were to, much the same way that we think this tidal locking happens with time, you can imagine that the spin axis might also in some sense correspond to how long something has been in its present position. At least the way I'm looking at it. I'm not sure that there's any actual solid explanation for why these things are tilted the way they are at this point. So that's very strange about those guys. The piece that I wanted to talk to you guys about to kind of close this down, one of the things that Mercury is most famous for is the precession of its perihelion. Anybody heard this story before? That's okay. I wouldn't expect that you had, but maybe you had, because this is famously one of the tests of Einstein's theory of general relativity.
Oh yeah, I heard.
So it's kind of, what's that?
Very
It's in the book, yeah, or in the workshop.
Yeah, it was in the workshop.
Cool. Yeah, it's worth mentioning. Of course, I'll probably throw water on it a little bit, like I always do. But let's talk about it. So, first of all, what the heck is a perihelion? Anybody?
I assume it has
Bonus
something to
points?
do with the sun.
Isn't it the furthest? I can't remember if it's the furthest or the closest point. It's from
All right, all right, all right, all right.
perihelion, like
There's
helium.
that's right. Perihelion and aphelion. Let's play with those words. So let's assume you're right that helion has to do with how close it is to the sun. Helios being the prefix of that word.
Oh,
Per versus ape. Which one do you think means closer?
I feel like probably pair.
Yeah,
Yes,
yeah,
it's the
absolutely right.
closest point in its orbit to the sun.
That's right. Nice. That's awesome. All right.
yeah. I assume it's like the same thing. It's the sun equivalent to forgetting the names for it now, but we have air. I'm forgetting the names, but they use it when they're trying to get stuff into Earth orbit.
And peri usually means like on top of. It's kind of a weird prefix. Trying to think of another example of it. Like periscope on a submarine is kind of like pokes out on top of the water. Yeah.
Paratroopers.
Different. That's para, but peri is I think the prefix here. Anyways, we're gonna get lost in the weeds. Mercury's orbit. I talked about it a little bit. I did want to mention. Sorry, I'm going to come back to this perihelion in a second. This is really really cool though. For you musicians out there, the rotation of Mercury with respect to its orbit is a 3-to-2 ratio, right? Whereas with the Moon and the Earth, it's a 1-to-1 ratio. So when you have 3 vibrations with respect to 2 on, say, a pair of guitar strings, you have what we call in music a perfect fifth. When you have 1 with respect to 1, you basically, or really 1 to 2, you would have an octave, right? This will matter to like the 4 or 5 of you that play music out there. All of the early Renaissance and Enlightenment scientists generally tended to be musicians as well. They were obsessed with finding these ratios. They literally believed that the solar system was full of music. They called it the music of the spheres because they were seeing these actual musical octaves everywhere that they looked. And so this is one of the really interesting features about Mercury's orbit. Now, the other one that's kind of interesting is, like I was saying, this perihelion thing. This is actually called the precession of the perihelion. So the closest point to the sun actually precesses. So it actually kind of moves around really, really slowly. So now the only reason that this is even noticeable is because Mercury has the biggest eccentricity of any of the planets. Yeah, because Pluto's not a planet technically. But if Pluto was, it would be bigger. But in the case of all of the other planets, in other words, it's a very long elliptical orbit, right? Relatively speaking. I think its closest point is something like 44%. Uh, I'm gonna mess this up. It's pretty far off center as with respect to the sun. I won't tell you the exact amount because I can't remember it. Okay, so now it precesses quite slowly. So people actually realize that it precesses, though. So how slowly do you think that it precesses?
Pretty slowly.
It precesses about 575 arc seconds per century. Now, how big is an arc second?
I don't know.
An arc second is about the width, if you held a human hair out at arm's length and you held it up against the sky, you would basically have measured out an arc second against the night sky. Remember how we divide the sky up into degrees, which are then cut down into minutes, and then they're cut down into seconds, right?
Oh, okay.
So we're talking about 500 human hair widths per century is how much Mercury's position, let's say at sunrise on the equinox or whatever the heck people were looking at, changed every century. So 575 arc seconds. Very, very little. Yeah.
So it's not the actual width of a human hair, but just it on the celestial sphere.
Yeah, on a celestial sphere at arm's length, like against the horizon, basically.
Gotcha.
Yeah, you can imagine like this would be like 180 degrees. That's a lot of human hairs, right? So first of all, it's remarkable because people realized that Mercury's perihelion was precessing, and they realized it all the way back into ancient times, basically into classical antiquity. People knew about this. There's stories about these Ptolemaic astronomers basically inheriting star catalogs that led them to believe this was happening.
Crazy.
It's totally nuts that people were able to make that precise of measurements. So, so people knew about this. Now, when all of our heroes from the first half of the course, Kepler and Newton and all these guys started trying to make these elliptical orbits work and mass and all of this, they actually dialed it in pretty good. They couldn't quite nail the precession of the perihelion. They would try to factor, like, why is the thing wobbling in the first place? Well, maybe it's getting tugged by other planets and stuff. They tried that. And they would factor all these things in that could maybe lead to it precessing like this, and it would still be off by like the tiniest bit. That residual bit was actually 43 arc seconds, something like that, 43 or 50.
That's a lot.
I can't remember. I should stop saying exact numbers. I'm going to get in trouble for messing something up. Somewhere on the order of 40 or 50 arc seconds. So 40 or 50, let's say, human hairs width against the horizon per century could not be accounted for using the Newtonian reckoning.
I just want to, we keep saying arc seconds and we comparing it to the width of a human hair, but then we're adding on top of that a coefficient, a multiplier for that. And so in my head, it's like, yeah, that's very small, but it's still like a measurable amount.
It is measurable.
So it's average width of a human hair is 0.0075 centimeters. So if multiplying that is 4.3125. So it's like 4 centimeters worth. Right. So it is a measurable amount.
It is a measurable amount.
But I just want to clarify that because for my sake, when I imagine you only
like 575 human hairs.
575 human hairs is approximately 4.3 centimeters.
Yeah, so something like that, right, over the course of a century.
Over the course of a century.
Yeah.
Yeah, so it would be perceptible.
Right.
Like
And so Newton's missing amount was probably something on the order of like half a centimeter or something, right?
Yeah.
Okay.
Sorry.
No, that's a very good point. It's a really good point. It's not outrageous, but over the course of a century, it's pretty amazing that people could even keep those kinds of records, So, okay. So, so along comes Einstein. We're going to deal with him a lot more next semester, of course, because it's very cosmologically significant. One of there was two really big pieces that won Einstein a place in history with respect to the preeminence of his new rendition of how gravity works. Well, relativity in general has two parts. One is general, one is special. Special has to do with the way that light behaves. General has more to do with the way that gravity behaves. And so this was really, Einstein's championship match with respect to winning the hearts and minds of scientists worldwide with respect to gravity.
Yeah, he made the theory of special relativity, and then general followed from that because of things that could not be explained with the special theory of relativity.
Yes. So this was a huge triumph for general relativity, which was the gravitational theory. Now, I would bore you to tears if I actually broke down for you how it was that Einstein accounted for those 40 extra arc seconds. But essentially, using a different model for gravity than this nice inverse square law that we taught you the first, couple weeks of class, you can correct for this tiny little variation. Now, how different is Einstein's theory of gravity from Newton's? I actually just made a couple of drafts right beforehand. So at 4 solar radii, there's a slight divergence. So the dotted line is actually Einstein's, and the solid line is Newton's. But when you actually go out at a distance beyond, say, 10 solar radii or so, you actually get into a point where Einstein and Newton completely overlap. This is why we teach you Newton for the most part when it comes to dealing with gravity, because they're basically the same thing. Einstein is really gnarly tensor math. It involves partial differential equations that are really difficult for us to convey. Newton's inverse square law is actually quite simple. And to be honest, NASA uses Newton's laws for the most part because they're just so much easier to work with. And as you can see, they basically tell you the same thing for most situations. Now, the deviation turns out to be great enough for Einstein to make up those extra pieces of the puzzle. So, one possibility to explain Mercury's perihelion is that we didn't understand the math of gravity very well. That's the most popular opinion for why that happens. Maybe so. There might be another explanation, though, that I want to share with you guys before I let you go. So, prior to Einstein, people were trying to solve this perihelion issue. And several astronomers, including some very famous astronomers, like the ones who discovered Uranus, proposed that you could make sense of this perihelion if there was another planet inside the orbit of the sun. They actually were so sure, and they solved the problem, and they got all of the math to work out, and they accounted for the 43 missing arc seconds. And they even gave the planet a name because they were so sure that it was there. You know what they called it? Anybody? They called it planet Vulcan. It was very hot.
Right.
So they were sure it was there. They were like, that's it. That's where the 43 missing arc seconds are at. They're in this planet that's interior to Mercury. If there's a planet there, if it's this particular dimensions or whatever, it'll take care of the problem. Obviously, there is no planet there. They never found it. And so this left the rift right around the time that, in the 20th century rolled around when Einstein, came along and famously solved this problem once and for all. However, there's another piece of this story, which I want to. There's another piece of this, and honestly, I'm not going to probably have time to build this all out for you, so I'll leave you with the tantalizing possibility. It's recently been discovered that the sun has what essentially amounts to a solid body rotation of its core. So everybody, on paper, people believe that the sun is some sort of gaseous plasma, right? But for some reason, the core rotates as if it's a solid body. Maybe it is, but that's not part of the standard story, and I don't have time for that right now. Now, there's another funny feature about the sun, which is that its magnetic field inverts in polarity every 10 or 11 years, something like that. Which is weird. If you think back to how we talked about why in the world the Earth does that, I told you about this experiment, right? And I wanted to show this to you guys before we leave really quick, which is, known as the intermediate axis theorem. There's a Russian word for it too, which I'll butcher if I try to say it. Now, if the sun truly has a lopsided core, which results in it inverting its magnetic field every 10 or 11 years, that lopsided core would also be sufficient to act as the offset mass that might be dragging Mercury's perihelion along as well. So those are the two possibilities I see. They don't even have to be mutually exclusive, honestly. Perhaps Einstein was just tapping into the regime that didn't really differ from Newton ultimately that much anyways. And if Newton had known about the lopsided core, he might have come up with the same solution at the end of the day. We'll talk about it more on Tuesday, guys. I think this is Thursday, right? No class on Tuesday?
Thursday.
Oh, wow. Thanks for telling me.
Yep.
All right. Well, kiss a veteran, and I'll see you guys Thursday.